In this video, we're going to begin our study of electricity. Here we'll define what we mean by electric charge, and we'll also discuss Coulomb's law, which allows us to figure out the force that one charge exerts on another. Let's start out by talking a little bit about static electricity and the types of experiments that were done early on. First of all, when we're talking about static electricity, the word static means stationary. What we're really trying to do here is to differentiate this from continuous moving charges like the current in a wire. Okay? So here actually the charges can move, but they're ultimately going to just be stationary on objects. That's what we mean by static electricity. So let me give you an example of this. Let's say that we take a plastic rod, so just a rod-shaped piece of plastic, and I take that plastic and I rub it with a piece of fur. What we'll find is that the plastic will take on a negative charge and the fur will take on a positive charge after I rub the two together. It turns out though, if instead of a plastic rod, if I take a glass rod and I rub that with fur, afterwards I'll find that the glass rod is positively charged and the fur is negatively charged. So from doing this simple kind of experiment, physicists were able to determine that there are two types of charge, which we call positive and negative. By the way, that naming convention was created by Ben Franklin of U.S. history fame. So Ben Franklin arbitrarily said the charge on a glass rod when rubbed with fur is positive. Now, of course, Ben Franklin had no idea what was going on at the microscopic level. The electron wasn't going to be discovered for many, many, many years from when Ben Franklin was doing some of these types of experiments. So he just figured out that there were two types of charges and that like charges repel and unlike charges attract. So if I take the plastic rod and I charge it and I charge another plastic rod, I'll find they repel each other. Two charged glass rods would repel each other as well because it would be positive and positive. But the plastic rod that's been charged and the glass rod that's been charged will attract each other. By the way, if these were two different pieces of fur that I used here, I would notice that these would now attract each other. So what's going on here? Well, we now know that what's happening is electrons are being transferred from one object to another. So different materials hold on to electrons more or less tightly. And so when I rub two materials together, what can happen is I get a transfer of electrons. Let me talk about a device called an electroscope. An electroscope is simply a device that shows you that there is a net charge present. If you look at the diagram here, this is an insulator, so we've got metal connecting through here, but not connecting with this outer case because of the insulator. And then we have two very thin pieces of metal. So what's going to happen here is if I put a charge on the electroscope, those two metal leaves or gold leaves are going to be repelled from each other. Now, probably the way you would think about this most commonly is what happens if I actually contact the electroscope with a charged rod. So I take my charged glass rod or plastic rod and I touch it to the electroscope. And in that case, I'm transferring charge to the electroscope. And in that case, for example, if I touch it with a with a positively charged object, my whole electroscope becomes positive, and therefore the gold leaves are going to repel each other. The other thing that's kind of interesting though is you don't even have to touch the electroscope in order to see an effect on the electroscope. So notice if I just bring a positively charged object close to the electroscope, what's going to happen here is in the metal, the electrons are going to be attracted to this positively charged object. And what I'm going to find is those leaves separate from each other because of this charge separation. so that down here, since it's all positive, those leaves will repel each other. In that case, and we call that charge by induction, as soon as I remove this rod, the leaves would go straight back down because this is still neutral. You'll notice I haven't actually transferred charge to that object. So we say that charge is a fundamental property of matter, like mass. And here's what we mean by that. If you think about our fundamental particles, like electrons or protons or the quarks that make up protons and neutrons. If we look at an electron or a proton or a neutron or a quark, what we find is that they all have a defined mass. So every electron has the same mass. It turns out that every electron also has the same electric charge. So it's a fundamental property of matter. Protons have a particular charge, electrons have a particular charge, etc. One of the important ideas about electricity is the conservation of electric charge. Now, if you think about what do we mean by conservation when we talked about conservation of energy or conservation of momentum? And if you think about it, what we meant was that the total amount of energy doesn't change, or the total momentum before a collision and after a collision are the same. And that's really exactly what we mean when we talk about conservation of electric charge. The net amount of charge produced in any process is zero. So charge is transferred from one object to another, but the total charge before and after any kind of an interaction is still the same. We're not creating charge out of nothing. We're not getting rid of charge. It's not appearing or disappearing in a way that the total charge changes. Another interesting thing about charge is that charge is quantized. Remember that when you hear the term quantized, it means that the quantity comes in discrete amounts. So charge is quantized. What that means is that there is a smallest amount of charge, and you can't go smaller than that. And any amount of charge is made up of those individual discrete charges. So it turns out that the charge on a proton or the charge on an electron are the smallest amount of charge we have. And as we'll talk about in a minute, protons are positive, electrons are negative, but the magnitude of those charges is the same. So that's the smallest amount of charge that we can ever measure. Let's take a look at the following question. Can charge be created or destroyed? What do you think? Well, based on what we just talked about with conservation of charge, you might very likely be ready to answer no. But it turns out that charge can be created and destroyed. It just has to be created and destroyed in such a way that the net charge before and after is the same. So there's kind of a cool example of this that I want to just go through and talk with you about, and that's something called pair production. Pair production is something that happens when a high energy photon comes close to the nucleus of an atom. So N there just stands for the nucleus of some large atom. And we've got our photon coming in. So this is a high energy photon. And by high energy, I mean like X-ray or gamma ray. So we got our high energy photon coming in. And it turns out that what can happen if a high energy photon comes near to a large nucleus of an atom is that photon can spontaneously disappear, and in its place what we get are two particles. And those particles are an electron and a positron. Now, if you've never heard of a positron before, a positron is an antiparticle. Specifically, it's an anti-electron. And you may have heard of antimatter in science fiction. Antimatter is real. For every matter particle, like a proton or an electron, there is an associated antimatter particle. that has all of the same properties except it has the opposite charge. The other thing about matter and antimatter, if an electron and a positron meet, they will annihilate. They will once again produce pure energy in the form of photons. So what I want you to notice here is that this process does not violate conservation of charge, because we know that photons are neutral. They have no charge. So before this happens, the total charge is 0. Well, after that photon interacts with the nucleus and disappears, we get a positive electron, a negative electron and a positive positron have equal and opposite charges, so the total charge after this is the same as before. It's still 0. So conservation of charge is not violated. By the way, the other reason I wanted to just look at this example is that it's a great example to understand Einstein's famous equation, E equals mc squared. You really shouldn't leave a year of physics without ever seeing this formula and understanding what it means. So here, remember that c is just the speed of light, 3 times 10 to the 8th meters per second. And what Einstein's famous equation is telling us is that energy and mass are related, and specifically that energy can be converted to mass and mass can be converted to energy. So think about what's happening here. We've got a photon. We know the energy of a photon is h times f, where remember h is Planck's constant and f is the frequency of the photon. And then what's happening is that photon is disappearing. The energy of the photon is being converted into the mass of the electron and the mass of the positron. Now we can actually use this to see why it has to be a high energy photon that is required for pair production. Because if you think about it, the energy of the photon has to be greater than or equal to twice the mass energy of an electron. In other words, the mass of a positron is the same as the mass of an electron. So we've got to come up with enough energy to be converted into those two masses, the electron and the positron. And so if the photon doesn't have enough energy to do that, we don't get pair production. So in other words, the energy of the photon, hf, has to be greater than or equal to the mass of the positron and the electron, so 2m, where m is the mass of an electron, times c squared. What we find then is the frequency is greater than or equal to 2mc squared over h. And if we plug in the values, so I'm going to put in 2 times the mass of an electron for the positron and electron mass, times 3 times 10 to the 8th squared, speed of light squared, divided by Planck's constant, which is 6.63 times 10 to the negative 34th. And what we get is a frequency of 2.5 times 10 to the 20th hertz. So that is the minimum frequency required in order to get pair production. And again, that's an X-ray or greater photon. So the purpose of me going through this question was really twofold. First, to show you that conservation of charge doesn't mean you can't create or destroy charges, but you have to do it in a way so that the total charge before and the total charge after are the same. And then also just to give you an example of E equals mc squared. Let's look at the properties of electric charge. So first of all, the charge on a proton and an electron, as I mentioned before, are equal in magnitude and opposite in sign. And that has to be exact. The unit that we use to measure charge is the Coulomb. And here's what the charge on a proton or an electron are. By the way, in class, usually we don't go to more than 3 sig figs, so usually I'm going to just write this as 1.60 0 times 10 to the negative 19th. Now, you might ask, how do we know that the charge on a proton and an electron are exactly equal and opposite? Well, if they weren't, we would notice it. Because it turns out you've got about 10 to the 28th atoms in you. So think about the fact that each atom generally has more than one proton and one electron, unless we're talking about hydrogen. So you've got even more protons and electrons than this in you. If there were even the slightest difference in charge between a proton and an electron, then everyday objects would have an overall net charge. And of course, we know that everyday objects are neutral. So these really have to be exactly the same to many, many, many significant figures. Let's take a look at just kind of seeing how big is a Coulomb. Well, it turns out if you take a glass rod and you rub it with a piece of fur, the charge on the glass rod is going to be about 5 microcoulombs. So remember, what's happening here is that simply means that electrons are being removed from the glass rod and ending up on the fur. So the question is, how many electrons were transferred to the fur? Well, we can figure that out by just taking the total charge on the fur and dividing by the charge per electron. That will give us the number of electrons. So if the glass rod got a charge of plus 5 microcoulombs, we know that the charge on the fur would be negative 5. So negative 5 times 10 to the negative 6th coulombs. We divide that by the charge on one electron, negative 1.6 times 10 to the negative 19th. So that's coulombs per electron. And what you get is about 3.1 times 10 to the 13th electrons. Notice that that's 31 trillion electrons. So just doing something simple like taking a piece of fur and rubbing it on a glass rod, you are transferring an incredible number of electrons. And that's why, in general, when we're dealing with electricity, even though charge is quantized, we don't see that very much because there's so many charges involved in everyday situations. So again, this would be similar to you're walking, you scuff your feet on carpet in the winter, and then you touch a doorknob and get a shock. Again, the amount of charge that's transferred between you and the rug or then you and the doorknob, it's on this order of about, some number of microcoulombs. So just doing a simple thing like that, you are transferring an incredible number of electrons. Let's talk about the 3 different types of materials. We break materials into 3 different categories: conductors, insulators, and semiconductors. In a conductor, electrons can move freely within the material. That means that a conductor can carry an electric current. So obviously we make wires out of metal to carry electricity. It also means that thermal energy is easily transferred. So if you think about a really simple example, if I take a stove and I put a pot on it and start heating up some water, let's say, or some soup, and let's put a couple spoons in here. Let's put in a wood spoon and a metal spoon. Well, we all know that once that soup is hot, you don't really want to grab the metal spoon, but the wood spoon is perfectly comfortable to grab. Why is thermal energy transferred so much better in metal? Well, it's because of the fact that the outer electrons in the atoms in a metal are essentially free to move within the metal. So not only can they carry electric charge from one place to another, but they also simply can easily carry kinetic energy. So in the metal, as the electrons gain energy down in this part of the spoon, they easily move along the entire object and therefore transfer that kinetic energy, which is ultimately what thermal energy is. In the wood, though, and in insulators in general, the electrons are tightly bound to the nuclei of the atoms that make up the insulator. And therefore, electrons can't easily travel, let's say from down here up to some point up here. They really can't move. And therefore, an electric current can't pass through an insulator, and thermal energy is not easily transferred because you don't have the little electrons moving throughout the object. Semiconductors are an interesting category. They're just a couple elements on the periodic table that are semiconductors. Silicon and germanium are the two. And what's interesting about semiconductors is they're kind of in between conductors and insulators. What that means is if you take a semiconductor material like silicon and you mix it with just the right stuff, you can make it so that it can change between being a conductor and an insulator by just putting a voltage across it. And by the way, that's the fundamental thing that makes up transistors and ultimately integrated circuits. In other words, it allows you to make a little electrical switch that can be either turned on or turned off, and that's ultimately what's inside all computers. Okay, so semiconductors naturally are kind of in between. They're weakly conducting, but by mixing them with the right stuff, you can make them conducting or insulating by putting a voltage across them. And again, that makes them basically a programmable switch, which is what's required to make something like a computer. Okay, here's another question for you just to check your understanding. Can an insulator have a net charge on it? So oftentimes students get this one wrong and they say no, because it's an insulator. But of course the answer is yes. If you think about it, in the examples that I've talked about, such as taking a plastic or glass rod, taking a piece of fur, and rubbing the plastic with the fur, what I've said is that the plastic will end up being negatively charged, and the fur will end up being positively charged in that case. Now, obviously then, the plastic does have a net charge on it. So what's different about that versus a conductor? Here's the difference. If I rub the fur on just this end of the plastic rod, that is where the negative charge will reside. Notice that charge does not move throughout the object. So once I put a charge on an insulator, it's stuck there. It can't move. In a conductor, so if I had a metal rod and I put some negative charge here, it would quickly distribute itself equally around the entire metal. So the charge would be free to move along the surface and within the metal, whereas with the insulator, once you put the charge on there, it can't move. Here's another question for you. A 10 Coulomb charge and a 1 Coulomb charge are separated by a distance of 1 meter. Which charge experiences a greater electrical force? The 10 Coulomb charge, the 1 Coulomb charge, they experience the same force, or we need to know the formula for calculating the electrical force. Why don't you go ahead and pause the video, think about this one for a minute. Okay, well, I like to joke with my classes that this is really the test to whether you deserve to pass Physics 1 or not. Because the answer is C, and that's because of Newton's third law. Remember that Newton's third law is the one that people always state with action and reaction, but the better way to say Newton's third law is object A exerts a force on object B. Object B exerts an equal and opposite force on object A. So in other words, it doesn't matter what type of force that is, this always has to be true. So if I call this charge object 1 and this charge object 2, let's see, they're both positive, so I know they're going to repel each other. The force that charge 1 exerts on charge 2, which remember we would write as F12, the force that 1 exerts on 2, and the force that charge 2 exerts on 1, they must be equal in magnitude and opposite in direction. So I could write that F21 is equal to F12. Notice I don't have vector signs on those, so those are magnitudes. That's just saying the magnitude of the two forces is the same. Or I could write it in vector notation this way, that F21 is opposite, equal and opposite to F12. Okay? So we don't even need to know the details of the formula that allows us to calculate the electrical force. We know that the force that 1 exerts on 2 has to be equal and opposite to the force that 2 exerts on 1. So Newton's third law, still true and still important. Speaking of Newton, I want to just remind you of the universal law of gravitation. So we looked at this in first semester. We saw that the force that one mass exerts on another can be calculated by Newton's law of universal gravitation. And remember that in this formula, m1 and m2 are just the masses of the two objects. R is the distance between the centers, and big G is the gravitational constant. And we said that gravity is one of the four fundamental forces in nature. Remember that gravity is always attractive. So we never get repulsion when we're looking at gravity. Now let's look at Coulomb's law. Coulomb's law, which was determined by Charles Coulomb back in the 1780s, allows us to figure out the force that one charge exerts on another charge. Notice that it's mathematically identical to Newton's law of universal gravitation. Instead of our big constant g, we've got a constant k. Instead of the mass of each object, we have the charge of each object. And then again, we have the distance between the charges squared, just like we had the distance between the masses squared. Really, the only thing that looks different here is that we've got these absolute value signs here. And that's simply because this is just going to give us the magnitude of the force. We know that the charge can be positive or negative, and so that's why we put the absolute value signs around there, so that no matter what, we just get a positive value for the force. But that idea that the electrical force can be attractive or repulsive is important, whereas gravity is only attractive. Now, if we look at K, our new constant, K is a value of 9 times 10 to the 9th Newton meter squared per Coulomb squared. You'll notice that this has to be what the units are for K, because ultimately we want charge to be in coulombs, the distance to be in meters, and we need to end up in newtons. One of the things you'll notice is that this constant looks much bigger than the gravitational constant. And you might conclude then that the electrical force is greater than the gravitational force. It turns out that that's true, but you can't judge it by looking at the constant. Because remember, how big or small we made a coulomb and how big or small we made a kilogram is really very arbitrary. So if we really want to compare the strength of the gravitational force to the electrical force, it's not as simple as just looking at those constants. So don't forget about Newton's third law, as we just talked about. Remember that our force here can be attractive or repulsive. And we know, though, that whether both charges are positive or both charges are negative, or one is positive and one is negative, the force that one exerts on two and the force that two exerts on one are always equal and opposite. Doesn't matter which charge is bigger. So in other words, if this is charge 1 and that's charge 2, F12 and F21 are always equal and opposite, no matter what, no matter how big the charges are. Here, again, we would have repulsion, F12 and F21. And then here, of course, we would have attraction. Okay, so that's going to end this video. In our next video, we'll continue to work with Coulomb's law. We'll actually look at how we can figure out that the electrical force is a much stronger force than the gravitational force, and we'll start looking at how we can do problems with this law.